All right. So, do you guys remember what did we do 2 weeks ago? Let's see who has better memory than me. What did we learn in the class? Not 2 weeks ago, actually last week. Sorry, we just missed the Sunday class, not the last week's class. So we started with vectors and scalars, correct? Okay. And you don't have to be shy. I mean, you can say yes also. That also works. All right. So so let's do a quick recap of what we learned and what we know, and so that we can relate those concepts with what we are going to do today. So whenever we talk about a vector simply means a measurable quantity with a direction to it. So if I'm talking about this is a line segment which doesn't have any direction to it. It has a starting point, ending point, origin or termination point. If I add a direction to this becomes a vector. Or if I put a direction to it, it becomes vector. So, and that's the primary difference between vector and a scalar. So when you talk about a vector, it has two parts to it. One is the magnitude or the absolute value. If you're talking with respect to this line, or this is called distance. If I put an arrow, it becomes displacement, and it is called a vector quantity. So here you have magnitude, where you'll say, okay, this is the length of this line segment or a vector or displacement or whatever you call it. So you'll say, let's say this is a vector B. You'll represent this like this. Say, okay, this is the direction, and this length is, let's say, 5 centimeters. So you will say magnitude of this with pair of parallel lines is equal to 5. So then this says that, okay, this is a vector, and the magnitude or the length of this or the value of this particular vector quantity is 5, and then this arrow anyway depicts the direction. So basically any vector that we talk about, it has magnitude and direction. That's the starting point. Now then we also learned about the components of a vector. Let's say if I'm talking about a vector, I will say this is a vector. Let's say this is a vector A. This is my direction. So in the direction, and this is my vector. And magnitude of this vector is, let's say, 8. And let's say 13. So then we learned about the components of a vector, meaning how do I break it down into different elements. So this is where Pythagorean theorem came into existence, or we could relate to that. So okay, fine. If I visualize this vector, this is my magnitude from here to here. This, if you think of this around a coordinate plane, this is the displacement around the x-axis, which is called displacement along the x-axis, delta x, and this is my displacement along the y-axis, which I will call as delta y. So I have, this is my horizontal component, this is my vertical component. So any vector that you pick up, you can always split that into two elements. The displacement along the x coordinate and the displacement along the y coordinate. Even if your vector is here, like this, so you'll say, okay, fine, this is my displacement along the x-axis, and this is the displacement along the y-axis or y-coordinate. Why we are saying displacement? It's because we are saying this is my origin and this is my terminal point, and how much my x is changing, my x value is changing between the origin and the terminal point, and similarly, how much is my y value changing between the origin and the terminal point. So that's why it's called the displacement along the x-axis or displacement along the y-axis, meaning you're only concerned about this distance, be it from, even if your vector is, let's say, starting from here and ending here, as long as this value meaning the x component and the y component, x component and the y component, sorry, this is x component, this is y component. As long as between these two vectors, your x and y component values are matching, or the displacement along the x-axis and y-axis is matching, meaning in terms of the absolute value. As long as your delta x is matching between both the vectors, delta y is matching between both the vectors, they will be considered same, because the origin doesn't really matter. It just, any vector that you talk about, it only talks about magnitude and direction. And what is your magnitude? This length is your magnitude. This length is your magnitude. And similarly, this is the x component of that magnitude. This is the y component of the magnitude. This is the x component of this magnitude. This is the y component of this magnitude. So as long as your x and y components match or are same in value, regardless of origin or terminal point, the vectors will be considered equal or same. Again, I am repeating myself, any vector that we talk about, it has two parts to it, two elements to it. One is the magnitude and second the direction. As long as your direction is matching and your magnitude is matching, meaning the length of this line is matching, they will be considered same. And how this length is derived? This length is nothing but based on this and this, applying the Pythagorean theorem. As long as your this x component and the y component are getting you the same magnitude, and x and y components between the two vectors are matching, they are considered equal or same. I know I've been talking non-stop for the last 5 minutes, but a quick question to you guys. Are you guys able to relate to what I'm saying so far, or whatever we have learned in the previous class? Yeah? Okay. So, at least we know what is a vector, what is the meaning of a magnitude, what is the meaning of the x and y components, and how do we relate to vectors. And one inference that we have drawn from what we have learned so far is, we don't really care about the origin or terminal point. What matters the most is the magnitude and the direction. As long as these two are matching, meaning the length of these lines are matching and the directions are the same, we are fine. Now, there is another scenario that we will come across, and let's think about it. If I say, I have two vectors, okay? One vector is this, another vector is this, where I am saying the x component and y component of these two vectors are same. Let's say this is delta x, this is delta y. This is delta x dash and delta y dash. If I say that delta x is equal to delta x dash and delta y equals to delta y dash, do you think these two vectors are same? I'm saying the x and y components are matching here. And when I say x and y component, it's just the distance between the x component of the terminal point and the origin. Similarly here also, the distance, this distance, we are talking about absolute length. Okay? So, this minus this and this minus this. I'm saying the absolute length is same. Okay? Then, do you think they are same or they are not?
I think they are, because if the x and y components are the same, that means the hypotenuse would also be the same. And they're going in the same direction.
But they are not going in the same direction, isn't it? This one is going downward, this one is going upward.
Oh, okay. I thought there was like an arrow at the top.
Yeah, so they are parallel, the direction is the same. But, I mean, I would not say direction is the same. They are, I mean, if you visualize this in a coordinate plane, they have the same slope, but the direction is opposite. Here this is pointing downward and this is pointing upward. Yeah. So let's spend maybe 2 more minutes, okay, to understand how do you derive the x and y component of any vector. Okay. So let's say this is my vector A. This is my vector A. Okay. My origin point is, let's say 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 1 and this is 9. I'm not writing the numbers in between. So what is the coordinate of my origin point? It is 2, 2. Yeah. And what is the coordinate of this terminal point? Let's say this is probably 6, comma, maybe 8.5. Okay. So how would I write this vector? I will say my vector is A. So let's look at, first find out what is delta x here. Delta x is the displacement along the x-axis, meaning the terminal point minus the origin point. Difference of the x coordinate of the terminal and the origin point. So it will be 6 minus 2, which is 4. So this is 6 and this is 2. What is my delta y? Terminal point minus origin point. So it will be 8.5 minus 2. 8.5 minus 2, which will be 6.5. So if I have to write this vector, I will say vector, this is capital A, vector A is equal to, I will say 4 delta x comma delta y. This is how you represent it. So we will say delta x is 4 and my delta y is 6.5. Okay. So this is my vector A. Now let's look at other vector, which is, let's say, I will look at this. This is vector B. So this is A and this is B. Okay. My origin point is here. I would say probably 6, maybe 10. And my terminal point here is it's 1, 3. So in case of B, in case of vector V, what is my delta x? Delta x is nothing but terminal point minus origin point, x value. So terminal point is here 1, 3, and my origin point is 6, 10. So terminal minus origin. So it's 1 minus origin point is 6, x value. I'm just looking at the x coordinate right now, which gives me minus 5. And delta x here, I could have plotted it little better. I could have picked up the point here. So that would have been 2, 4. Okay. So 6, it will be 6 minus 2. So sorry, 2 minus 6. 2 minus 6. That gives me minus 4. So my delta x value is minus 4. Now similarly, if I look at the y component, delta y for this second vector B is nothing but the y value of the terminal minus y value of the origin. So y value of the terminal is what? 4. Minus y value of the origin is 10. That gives me minus 6. So here, if I have to write this vector, put the value of the vector, which will be delta x for this comma delta y, it is x is minus 4 and y is minus 6. So what you see here is, I'm just doing some cleanup activity so that you guys can relate to it. Now this is my vector B and my vector A is this value 4, 6. So you see a very striking difference here right away. When your vector is going downwards, your delta value changed from positive to negative. So that depicts, if you see a delta x, delta y being negative versus positive, you can understand whether it's an upward slope or a downward slope. Yeah. So even if, let's say here I took, it was 6.5. So if I would have picked up a point such that the difference was only 6, matching with this one, even if my absolute value for x, I mean x and y component would have matched, still the sign depicts the direction of the vector. This is where it says, even if your magnitude is matching. Now let's look at the magnitude of this. Let's assume that this difference was also 6 only, okay? I mean by picking up the right point. Let's say this was also 8. Okay? So both x and y components were -4, -6 for B and 4 and 6 for this one. Now if I have to find out the magnitude, how do I do? This is simple Pythagorean theorem, right? So this will be this square plus this square root. So if I'm talking about A, the magnitude of A will be nothing but square root of x square, x component plus y component. My x component is 4, this is 16, plus y square of this one, this is 6, so this becomes 36. So magnitude of A, or the length of this, is square root of 52. Similarly, if you look at this guy also, you will get the magnitude of B also as same. -4 square gives you a 16 and -6 square gives you a 36. So this also becomes 52. So here what you see from this is your magnitude of both of them is same, meaning the length is the same. What is differentiating them is the sign of the x component and the y component. Is this part clear, or I'm getting you guys more confused? And you should not have any hesitation in saying no, sir, you cannot understand, because your teacher is not always right. Let me repeat myself just quickly for 30 seconds. We picked up two vectors. One was facing upward, one was facing downward. So we know that we can break down this vector into x and y components, and x and y components of the vector is nothing but the displacement along the x-axis and the displacement along the y-axis respectively, meaning how much is your x value changing, or what is the difference in your x component, in the x coordinate between the origin and the terminal point, meaning terminal minus origin, that gives you the x component. Terminal minus origin y coordinates value gives you the y component. So that is how in this case, when it was an upward slope, you saw that okay, your x and y value both are changing in a positive direction in the first case. So you got your x and y component, which is nothing but the displacement along this x and y axis, as 4 and 6 positive. Similarly, when you looked at the second vector, which was facing downward, you saw that your origin is at a higher value of x and y, and your terminal point is at a lower value of x and y. That is how, by subtracting from the terminal to origin, you got negative x and y component. Because to calculate the negative, x and y component, you have to always subtract the x coordinate value from terminal to origin for both the coordinates x and y. So that is how, in the case of a downward facing vector, you saw that your x and y components are giving negative value. And what is the magnitude? Magnitude is nothing but the length. So be it facing downward or upward, the length of your side doesn't change. That is how Pythagorean's theorem says that the length of this line versus length of this line, which is just a square root of the squares, right? That is always positive. So your magnitude will not tell you if there is a difference. Your x and y component of the vector tells you, because that is what determines the direction of your vector. Is this part clear or not? Chris, Dave, are you forced to be agreed, or I'm able to explain this?
No, sir, I understand.
Understand?
I understand.
Okay, wonderful. So this is, so any vector that you talk about, you have to always look at what are the key elements of a vector. And vector is a very simple creature which has only two body parts. One is the magnitude, and second one is direction. Now direction again has two babies to it. One is the x component and the y component. So your x, if you're looking at a vector, this is a vector where one thing is the magnitude, which is nothing but the length from here to here, and second part is the direction, which comes from your x and y component. And here if you see, the direction has, the x and y component has to be determined by understanding the difference between the terminal and the origin point. So if your terminal is at a higher point, meaning it's in the positive direction, you will get the difference, this part as positive or negative depending on whether it's upward slope or downward slope. So this brings us back to the next topic that we wanted to cover today. So let me quickly call out the topics that we wanted to cover, and then we will see what all we know versus what we need to know. So first thing we wanted to know was vector magnitude from graph. So by plotting or graphing a vector, how do you find out the magnitude? Second is scalar multiplication. Third is adding and subtracting vectors, and fourth is parallelogram rule for vector addition. So let's see how much we can cover. So first thing is finding out the magnitude of a vector from a graph. So that is pretty straightforward. You guys have not learned, you have actually played with Pythagorean theorem enough by now, right? That would be my assumption. Pythagorean theorem is something that would have gotten memorized better than your own name itself, correct? Is that a correct statement? Yeah? And sometimes you guys have to spare me for those dad jokes. So I'm just asking. Nobody forgets his or her name. I'm saying Pythagorean theorem you would have dealt with enough. I mean, enough to be tired of. Now, so what we are trying to figure out is how to find out the magnitude of a vector from graph. So it's very simple. This is something that we did already. Let's say this is my vector, and when somebody gives you a vector, what do they give you? They will say, okay, I have a vector A, or let's say a vector C with something as x component. Let's say x component is -3 and the y component is 8. Okay, and they say find out the magnitude of this vector. So the first thing that you would figure out is, okay, x component is -3 and y component is 8, meaning x value is decreasing. What do I mean by decreasing? Meaning my x value is decreasing from origin to terminal, meaning x value, let's say this is my origin and this is my terminal, let's say. If I say this is -3, meaning x value of this point minus x value of this point is giving a negative. In this case it will not, right? Because you see that your correct. So if you try visualizing this, right? Here I'm saying my x value is negative. This doesn't seem to be the case because my x value is -3. What is the scenario? This is 1, 2, this is 3, this is 4, this is 5, let's say. Okay? Meaning my starting point's x value is bigger than my terminal point. Meaning my terminal point is somewhere here maybe. Okay? And then my starting point is somewhere here. Let's say here. In this case, let's say if my vector is like this, then what do I see? My x value here is probably what? 1, 2, 3, 4, 5. And my terminal point's x value is 2. I'm not worried about the y value right now. But just by looking at this negative value, you can see that, okay, fine. My vector is pointing towards, it is northwest. Yeah, it's pointing northwest. Now, how about this guy? Y is positive, meaning y value is changing between my origin and terminal point. So this seems to be correct. Maybe this is 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Now, if you look at this, my y value is here probably 2, and in this case it became 10. So yeah, terminal minus origin, 10 minus 2, 8. This is correct. X component, terminal minus origin, 2 minus 5 minus 3. So just by looking at the x and y components of a vector, you would be able to visualize how your vector is looking like, or how you can plot it. Is that making sense? This is simplest of the math, but it has more to do with the visualization part of it. Okay. Whenever you look at, if I say I have vector b, which is 2, 1. Just by looking at this, you can see, okay, my x value is increasing, my y value is also increasing. Both are positive, meaning increasing. If you look at this one, my x value is negative, meaning my x value is decreasing, and y value is increasing. What are the scenarios? When you're talking about this, you're talking about x value increasing. So origin point is somewhere here, destination is somewhere, terminal point is somewhere here. That is how it can increase. I mean, maybe this graph is not correct. I'm saying you can clearly visualize the trend. Now whether this will be this steep or this shallow, that will figure out by looking at the other aspect of it. And good thing about vector is, you don't really have to worry about the origin and destination. You can as well shift this vector from here to here. As long as the magnitude remains the same, the x and y component value remains the same, you're still good. Yeah? So this is the visualization part of it. Now what we're trying to see is how to find out the magnitude of a vector from the graph. So we just had the value of the vector, right, x and y component, and we wanted to find the magnitude, meaning the length of this line. How do you find it out? Very simple. Uncle Pythagoras has given us the solution for this kind of problem always. So here, by looking at this, let's say if this is my case, if I'm talking about this one, so my x component is minus 3, meaning here to here is minus 3. And y component is 8, meaning here to here is 8. Apply that in Pythagoras theorem. Let's say this is the magnitude of C. So I'll say magnitude of C is nothing but square root of this square plus this square. So minus 3 square plus 8 square. This gives me 9. This gives me 64. 7 square root of 73. This is my magnitude. So here, the good thing is, if you have to just find out the magnitude, you don't really have to worry about the sign, because be it a vector like this or a vector like this, when you look at this part, the x component and the y component, you are essentially doing the square of the x component and square of the y component to get the magnitude. So here, whether it's minus 3, meaning it's the x value decreasing or x value increasing, be it minus 3 square or be it 3 square, in both the cases it doesn't make a difference. It remains the same. Yeah? So, just by looking at any vector, let's say, if I just randomly say, okay, find out the magnitude of a vector W with values given as minus 12 and 5. It will just find out the magnitude. So first thing you will say, fine, I have the x and y component already given. If I have to only find out the magnitude, I don't need any fancy thing. I'll get the square of Yadev.
Sir, can I leave the call? I have some things that came up. I'll just watch your YouTube video later.
Sure, no problem. It's okay.
Okay, thank you so much, Sir.
No worries. So I'm saying, if I just have the x and y component of a vector given, I don't really have to scramble. I have to just visualize, okay, even if my visualization is not right, for me, this is my magnitude. And that is made of this component and this component in a Pythagorean theorem. This square plus this square, whether it's negative or positive, I don't care. Minus 12 square is equal to 12 square. So we don't really have to worry about whether I am plotting the right direction or not. If you have to just find out the magnitude, if you have to graph it, that is when you will think, okay, my x value is decreasing between my origin and terminal points. Meaning, if this is my graph, you start painting this in your mind okay, my x value is decreasing, meaning if my x value origin is more, it becomes less. Okay, minus 12. This is the difference of 12. Okay, fine. Y value is increasing, meaning if this is my origin point and this is my terminal point, y value is increased. So here my x value is more and here it is less for the terminal point. So this is my terminal point. That is how this can be negative 12. And y value is increasing. So my terminal point is higher than my origin point. So that is this graph looks to be fine. So basically we have to always visualize that, and once you are able to visualize a vector by looking at the values, it will be a cakewalk. So it's always about how do you wrap your head around the information that you have at hand, and then how do you kind of picturize that, how do you plot it, how do you graph it in a scratch pad to be able to get to the solution of this one. So finding out magnitude from a graph or from a vector value should not be a problem unless you guys think otherwise. Let me stop here before I proceed further. Any questions so far, Prisha and Chris? Is this looking clear?
Yes, sir.
Okay. So this was the next topic that we wanted to cover. Let's go on to the next one. Scalar multiplication. So if I talk about scalar multiplication, what do I mean by that? First of all, what is a scalar? Just a number. It has no, it's a directionless number. That's what is scalar, correct? When I'm just studying without a goal in my life, that is when I become scalar. When I know that if I study, I want to become a scientist, I want to become an engineer, I want to become a doctor, I want to become a lawyer, that is when I become a vector. I know this is not the right analogy, but that is how we relate it in layman's term, correct? So, I'm saying multiplying with scalar. Essentially, this whole subject, this whole chapter is around vectors and how do you deal with vectors and the scalars. Now, one thing we are very clear about is scalar is something which is directionless, meaning it's just a number, pure plain number. If I say 4, this is scalar. If I say 4 with a direction, that is a vector. This part is clear, right? Now, what is happening here is multiplying scalar with a vector. So let's say this was my vector A. Now, since we know that every vector has two components to it, x and y component. Let's say delta x comma delta y. Or to even make your life look much easier, I will say I have a vector A with x component as 2 and y component is 3. When I say so, what I mean is my x value is positive, my x component is positive, y component is also positive. So in our mind we can picturize this as, okay, it will be a vector like this. But because when my x value increases, my y value is also increasing. It's a positive slope if you compare that with a linear equation kind of scenario. Yeah. So this is my vector. Now somebody says multiply this vector with a scalar. Scalar is nothing but a number. So when you multiply a vector with a scalar, or in simple terms just a number, what happens is you have any vector that you talk about, you have x component and you have y component. When you are multiplying a vector, what you are essentially doing is you are multiplying the scalar with your x component and your y component as well. This is how you would want to relate. It's as simple as this is your bracket. In your bracket you have 2, 3. You said this is your vector A. When you multiply this by 2, you are essentially saying, okay, I am multiplying this by 2. So what's happening is you are multiplying, let me not multiply by 2, you already have a 2 in here. Let's say I am multiplying by 4. So when you are multiplying the vector by a scalar 4, you are essentially multiplying the components of the vector also by 4. Meaning your x component gets expanded 4 times, your y component also gets expanded 4 times. Is this part okay? See, this was my vector, right? This is how you deal with the equation, right? This is an equation kind of a thing. You are saying multiply 4. So I have to multiply 4. Yep. So essentially what this translates into is you are multiplying that scalar with your x component of the vector and you are multiplying this scalar with the y component of the vector as well. Yeah. Now let's look at a bigger picture. I know this sounds philosophical, right? People say don't look at things in a narrow view, with a narrow view. Look at the bigger picture. So let's look at the bigger picture. Now let's say this was my attempt to throw this pen. Let's go to a board. So this was my, let's say this was my vector, okay, W, where I'm saying this vector equals x component is 2 and y component is 1. Meaning my x value between origin and terminal points is increasing by 2 and my y value between the origin and terminal point is increasing by 1. So I'll plot this here. So what I will do is let me make it little simpler. So let's say this is my vector starting from the origin of the coordinate plane. Okay. So this vector W is 2, 1, meaning when it's moving by 2 points on the x-axis, here to here, let's say this is 1, this is 2, and this is, let's say, 1. If I multiply this vector W with 2, or let's say 3, so I'll multiply by 3 here also. Let's see what will happen. So this was my original vector W, okay. Now multiplying this vector by 3. So what will happen? My x component will become 3, 2, meaning 6, and y component will become 3, meaning this will translate into other vector with the x component. This, let's say this becomes V, which is green. Okay, this becomes 6, 3 because we multiplied this vector by a scalar 3. This becomes 6, 3. So if I think along this line, let's say this is 3, this is 4, this is 5, this is 6, this is 2, this is 3. Now look at this point, this one in isolation, 6, 3, meaning my x component is changing by 6. So we are saying, look at this, and y is 3. My drawing skills I am using, so you will probably not like it. But what you will see is when you multiply this by another scalar, this same vector got multiplied by 3, or the magnitude became 3 times. If you want to look at it mathematically also, it will be the same. If this is 1, 2, this was the vector, right? If you look at the magnitude of this guy, it will be what? 2 squared plus 1 squared square root. This will be the magnitude of W, which is nothing but 2 squared plus 1 squared square root of 5. Now you look at this guy. Magnitude of this guy will be what? I'm calling this a V. So magnitude of V will be what? The x component, which is 6 squared plus y component, which is 3 squared. So this becomes 6 squared is 36 plus 3 squared is 9, which is square root of 45. I can take 9 out, I can say 9 into 5, or 9 is nothing but 3 squared into 5 square root, that gives me 3 outside square root of 5, 3 times of this one. So what happened was, when you multiply any vector with a scalar, your magnitude gets multiplied that many times, and that's natural, right? If I have 2 mangoes, if I multiply that by 3, it will become 6 mangoes, correct? Same thing here. Your magnitude became 3-fold. Now, what essentially happened with your x and y component? Same thing. Like what we see visually, mathematically, optically, whatever you call it. Same thing, nothing changed. Your x component multiplied by 3, your y component multiplied by 3. So, this got extended 3 times. Now, there is an interesting part to it. if I multiply it by 3, that is wonderful. What if I get a mischievous intent and I multiply this by -3? Because -3 is also a scalar, right? It doesn't have a direction. It's -3. So here what will happen is, when you multiply this by -3, everything flips down, and this will have the same length, because when you multiply by something, your overall x and y component length will remain the same. So your magnitude will become 3/4. The length of this line and length of this line will be the same. But when you are multiplying by -3, your x component gets multiplied by -3. So this becomes -6 and this becomes -3. This gives you a view that, okay, if you are multiplying by a negative number, your vector flips by 180 degree and goes in that direction. Did you guys find this digestible before calling it interesting?
Yes, sir.
Pretty sure with that? Yep. Okay. So this is how you visualize. See, if you ask me, are we learning something complicated? No. This is the visual side of math, where you guys have learned what is Pythagorean theorem. You guys know what is a coordinate plane. You know how do you identify different points. Vector brings a different dimension to that learning, where we look at the vector without any bias for the origin or ending point. We just say, okay, this is the direction and this is the magnitude. Now whether the same magnitude is starting from here or starting from here or starting from here, doesn't make a difference. Vectors are immune to the origin point for itself. Same magnitude 3 in this direction could be from here, could be from here, could be from here, doesn't matter, as long as the length of your lines are the same and the direction is the same. Or in a more refined way, you can say as long as your slope is the same and your length is the same. So this slope is a positive slope, this slope is a negative slope. So here, if you want to relate that to your understanding of the linear equation or the y-intercept form of a linear equation, you would be able to relate it better. But it's the same concept with a different package or in a different package. Yeah. All right. So let's see what all we covered. So we covered what is vector magnitude from graph, and then multiplying a vector with a scalar. Are you guys clear about what did we mean by scalar multiplication and how that reflects in the way we visualize things? Or do you guys want me to get my hands even more dirty? Getting hands dirty is very good, okay? So when I teach you guys, right, the first thing I do is I wash my hands, because I practice maths to get my hands dirty. And I would expect you guys to do the same, because math is not a subject to study, it's a subject to practice. Okay? Alright, so this part, I'm assuming that you guys are clear, and if you're not clear, let me know. Now let's look at one more thing, that is called adding and subtracting vectors. Okay? So before I try explaining that, let me pick your brain to understand what would be your interpretation. If I say I have vector A and I have vector B, when I say add them together, what does it mean? In whatever shape and form you want to explain, that's okay. And trust me, any definition is not wrong, any answer is never wrong. Okay? So tell me if you want me to conceptualize this in a more visual form or more expressive form rather than mathematical form. What would be your interpretation by when you say add two vectors or subtract two vectors? Give it a shot. Chris and Prisha, both of you are Hindi speaking. So, one more time. Kuch to bolo. Me? Okay, alright. I mean, that was a bad joke, like I always say. My kids say that your jokes are bad and they call it dad jokes. Alright, so let's come back to this. I have vector A, which is here. I'm not giving any other detail, okay? Or let me say this, okay? This has x1 as the x component and y1 as the y component. I have second vector B with x2 and y2. Okay? No confusion? I'm saying A plus B. Okay? Am I saying something complicated? No. Now, let me give you guys another lame example. If my body consists of two things, okay, 2 hands and 2 legs, and one of my friend's body consists of 3 hands and 4 legs. I know I have not seen anybody like that, but I'm just, for the sake of mathematics, we are doing so. So if I say add me and my friend, what will you add? My identity is 2 hands and 2 legs. My friend's identity is 3 hands and 4 legs. When you say add these two people together, what you will get to see when you add me and my friend? Two unique creatures on the earth. What will you see? You know me only with 2 hands and 2 legs. You know my friend only with 3 hands and 4 legs. There is no other property, there is no other behavior that you are aware of. So you say, okay, fine, I don't know you, I don't know your friend. I only know you have, Birendra has 2 hands and 2 legs. And Birendra's friend, BF is not the right word, I'll say my friend's name is F, friend. So 3 hands and 4 legs. You will say you guys have no other identity. I only know you by your hands and your legs. So if I'm adding you guys, I'll only get to see this many hands and this many legs being added. Correct? Okay. So same thing here. These are the hands and legs of this vector. These are the hands and legs of this vector. When you're adding these two vectors, what you're doing? You're just adding the hands and legs. That's it. Meaning, when you're adding them, you're adding the x component together and you are adding the y components together. Yeah. You will not add apples to oranges, right? You will not say that, okay, Virendra and his friend together have 2 plus 3, 5 plus 2 plus 4, 6, 11 hands or 11 legs. You will still say 2 plus 3, 5 hands and 2 plus 4, 6 legs. Correct? You will not add apples with oranges. You will not add x with y. You only add the x components together, you will add the y components together. This part clear, right? I might be sounding like I'm teaching toddlers or the babies, and interestingly you guys are like babies for me, okay? So I will keep on treating you guys like that. So that's why I am probably giving some lame examples at times, but it will probably help you relate because no, simple things are better. Yeah? So up to this was clear, right? Chris? Okay. See, I'm a very greedy teacher. Unless I see some reaction from you guys, I don't feel like going forward. Okay, so coming back to the point. Now, I said that, okay, if you have two vectors to add, you will add the x components together, you will add the y components together. That becomes your resulting vector. A plus b, let's say if this becomes c, a third vector, it will become something like this. Same thing applies if I try subtracting it. If I say a minus b, what would it mean? It would mean A minus B. So x component of A minus x component of B. So A minus B, if A minus B becomes a vector D, that would be equal to x component of A minus x component of B, comma y component of A minus y component of B. Yeah. Now, there's nothing so very interesting about it. You will say, this is kids play, and that indeed it is. Now the interesting part of that is, how would you relate this in a visual world? Now let's come to a point where we are trying to visualize this, okay? And I'll stop it there, okay? I want you guys to think about what exactly happens when you do A minus B. Let's say this is my A, okay? This is my A, and let's say this is my B. If I say A plus B, remember one property that we realized or understood or learned is that origin of any vector doesn't matter. Meaning, if I just shift this guy, move it from here to here, so that it connects to the tail of this vector connects to the head of the previous one, I'm still not doing anything mathematically wrong, because vectors gives me the flexibility that my origin doesn't matter. As long as I'm just shifting it, I'm still fine. Does it make sense? I'm repeating myself. The vector gives us the flexibility that when you move a vector from one place to another, as long as you're just shifting it, you're still fine. Because you're not changing the direction. See, it was here. I just moved it here. So I did not change the magnitude, I did not change the direction also. I did not make it here this way. I kept the direction same. I kept the slope of this line segment same. I just shifted this guy. I said, I don't like this guy being alone. I want this guy to be a friend with my previous vector. So I connected the tail of one vector with the head of the other vector. So now let's say, I'll probably stop it here, okay? Now what this means is, when you connect these two vectors, let's say this is my third vector. By adding these two, what happened? It looks like a journey. You started from here to here with vector 1, vector A, and then the journey continued from there to this place. So this is the final place. If you visualize this as a vector, vector says what? What is the magnitude and what is the direction? What is the x component, what is the y component? So these two resulted into this third vector C by adding A and B. And if you do all the mathematical calculations with this, which we'll do in the next class, I don't want to stress you guys out, but if you think of this as the resulting vector, the x and y component of this vector, the C vector, you will see that will be equal to this plus this. You'll be able to mathematically relate this also, as well as think of it visually. Similarly, if I say A minus B, now if you recall what we were doing a little bit ago, a negative B, vector B, if I multiply this with a factor minus 1, what I'm doing is, I'm multiplying the x and y component with minus 1. What does it mean? If my x was going upward, it will start going downward. So it flips by 180 degrees. So if I multiply, if I say A minus B, so essentially what I'm saying, A plus minus B. And this minus B is reverse of this. Same magnitude, but the direction is opposite. So A minus B will be same as this. And then this is the resulting vector. So as long as we can appreciate how the resulting vector C comes by putting A and B together, by adding the two things together, subtraction is nothing but just a scalar multiplication to the second vector, and works the same way. So we will see, this is the interesting part of the vector. So far whatever we did, there was nothing new that you guys learned. Now what we are doing is adding a visual element to it, so that we can relate and kind of put all the concepts of vector together to play with this. So we'll talk about this in more in detail, mathematically how this is proven by connecting the head and tail together, and how the subtraction works along with this. And the next thing that we'll learn would be nothing but relating that to a parallelogram. That will be nothing new. As long as we understand the addition subtraction part of vector, parallelogram is just an extension. You don't really have to worry about it. It's just another narrative built on the same concept. So this is where I will take a break and ask you guys that whatever we did for last 1 hour, was that understood well, or I just created confusion for you guys on a Thursday evening? Yeah?
I understood it.
Okay, wonderful. Then me not changing my dress after coming back from work was fruitful. Okay, alright, so I'll let you guys go, take some rest, and see you guys in less than 48 hours.
Thank you, sir.
Alright, bye bye.
Thank you, sir.
Bye bye. Good night.